Okay. Good afternoon, ladies and gentlemen. Shall we start today's the seminar series? And thank you very much to attend to the today's two sessions. And today we are very happy to have the very famous professor on the surface chemistries, and his name is the Professor Hidde Brongersma, and from the Eindhoven University of the Technology and Imperial College. And for me, he's the ION-TOF or the Calipsos. And then in the custom, I would like to briefly introduce him. And actually, he studied physics and chemistry at Leiden University, where he also received the PhD. And then after postdoc at Caltech, he joined Philips Electronics, where he was at the development of the low energy ion scattering we call LEIS. And after the Philips, he appointed as a professor of the chemistry of the Leiden University, and then he also has opened a company named Calipso, and very recently he occupied an honorary professor at the Imperial College London. And the research work is covered a variety of the area, but the most famous one is today's talk on the low energy ion scattering, which is the new tools for the analysis of the surface. And because of this, he received several number of the award, but maybe you can see it on the pamphlet, because time of today's talk, the time is very limited. So I'd like to start to the presentation. So today's Professor Brongersma's talk is on the high sensitivity, low energy ion scattering, new tools in the understanding of the performance of the catalyst and the other sub-nanometer materials. So thank you very much for the presentations.
Thank you very much for the kind introduction, and it's for me a great pleasure and an honor to be able to speak at this place. Why it is especially fun for me is that later this year there will be installed here at Kyushu University this low energy ion scattering technique. So all the examples that I will talk about, say in a few months' time, you will be able to do similar things or even much nicer things here in Kyushu. So I look forward to hear about that. The ion scattering, it is a technique which can selectively look at the outermost atomic layer of the surface. That is where chemistry takes place. And that is why it is so very important. I'm always half a chemist and half a physicist and half something else. But for chemists, it is very important that where the activity takes place, that is what you can analyze. And that's why it's so much fun. On the one hand, it is something to look at the top layer, the first atom layer, and I'll show you, you can also do look in depth. And we have developed many new applications, and since ion scattering is kind of unique, it has some unique features that we think no other technique has, what I will do is go through a couple of these applications just to give you the spirit of what is fun with this technique. So it's not just one topic, but I'll go a little bit from one topic to another just to give you some ideas on that. Now, let me go down. I'll first introduce how does it work. Well, it's a very simple technique. It is basically a billiard ball game. You come in with atoms of a certain mass and you scatter that atom, that ion from the surface. You come in with a certain energy, and just by transfer of momentum, you get slower. And if you collide with something very heavy, you come back with all the energy, like a tennis ball against the wall, it comes back with all its energy. And if it hits something of almost the same mass, it will collide and almost stop. So the energy after scattering depends on the mass of the surface atom. It's a mass analysis, but a mass analysis of the outermost atomic layer. So, for instance, here you see an example of neon scattering from an alloy. So it has iridium, rhodium, cobalt, manganese, vanadium, potassium, and so you get them all separate and you see how much is in the top atomic layer. It is a quantitative technique, and for people who are in surface science, we would say there are no matrix effects, which means the sensitivity is determined by the atom and not by the neighboring atoms. Typical energies, lateral resolution is not so good, although in depth you look very accurate. Laterally it is broader. This is the spectrum that many years ago really got us going. We had been doing ion scattering for a long time, and I'm also a little bit professor of catalysis, and so we would look at real catalysts. And we started off by looking at palladium, platinum nanoclusters on a carbon support. And carbon is very, very rough, so it's difficult to measure. If you would do that with a technique like XPS, there was so little on it you don't see anything. You don't only see carbon. Well, in the old days, we could see palladium, we could see platinum. However, the number of ions that I needed to get this spectrum was a lot. 10,000 nanocoulomb, which means actually I kill the surface before I get my spectrum. However, we developed a new instrument, and there you see the new instrument. Instead of 10,000, I need about 5 nanocoulomb. So very much less ions. And at the same time, you see this looks much nicer. Okay, that is the improvement that we made by having a team of about almost, effectively 600 man-years. That means 600 persons during, say 30 persons during 20 years to develop that technique. Also, what is interesting to see, you see this background. Very nice flat background. I made that myself. Why? Because the sensitivity of the technique is such that we can see promoters. So it's not only palladium, platinum, but there are tiny additives. But they are secret, so I cannot show you. So just because here there are people who know a lot about catalysis, I don't want to give them great ideas, so I just made that background myself here. But you see the statistics is much better, and that is why now, even for very rough catalyst, we, in a standard way, we can do analysis. How does it work? Well, you make ions here in an ion source, you accelerate them, whoop, whoop, whoop. They hit the sample and they scatter back. So they come in and you scatter back in a cone. And because it's a cone, they all have the same scattering angle. And you collect a lot of the ions. Then, when the ions scatter back, this is an electrostatic field. Fast ions go to the outside, whoops, and end up here. Slow ones are deflected. So here at the end, I get a spectrum in energy. So instead of scanning through, which takes time and I kill my sample, I do parallel detection. These two combinations make that our sensitivity is maybe, I generally say, a factor of 3,000 higher than of similar machines in the world. And a factor of 3,000, I mean, I would say I can make my students work very hard. They can make them work twice as hard or 3 times, but 3,000 times harder is difficult. So it's nice to have a machine that does that for you. Now, quantification is a long story, and for those who are really interested, I can say, okay, that you can find a publication on it. I'll give you just one example to illustrate how you do quantification. And this is the absorption of bromine on top of tungsten. So just flat tungsten and I absorb bromine atoms. In the beginning I do ion scattering and it is pure tungsten. So okay, I get a high tungsten signal. And when I absorb bromine, the tungsten signal goes down and the bromine signal goes up, linearly. Why? Because I look only one atom deep. So at the surface it is either tungsten or bromine. So the coverage of tungsten plus bromine is 100%. I call it 1. And so if there is less tungsten, there must be more bromine. And that kind of quantification makes it so very simple, because you don't have to think about contribution from second, third, 20th atomic layer. It's just everything going on in the top layer. If you do organics, like self-assembled monolayers, we analyze the top layer. So here the yellow ones, here the backbone, there the orange ones. And so it is very complementary to other techniques that look deeper, like SIMS and XPS, where you see, say, maybe the whole molecule. And by combining the two, you understand much more about organic molecules, how they orient and what they do at a surface. What ion do I use? Well, it depends a little bit. Sometimes for light elements, if you want to scatter back, you need something that is still lighter. You can only scatter back from something that is heavier. So we use light things like helium-3 and 4 for organics, polymers, etc. But sometimes we go to very heavy ions, and I'll show you an example. Your mass resolution gets better, sensitivity gets better, and so for catalysts we very often use these ones like neon and argon. This is an example where we do, that's together with various companies also in catalysis, we look at catalysts that have heavy elements, and sometimes they have platinum and gold. And the problem is that the isotopes of platinum and gold, they overlap. They are heavy and they are not easy to separate. So, but here we use krypton 84, so a very heavy ion, and then, yes, you can see that even on a real catalyst, if it's clusters of platinum or gold, we can see the difference and then deconvolute it. Now, the last information we need before we get to real applications is that, yes, the ions come in, they scatter from the surface. Many of them go deeper and may scatter back there. However, helium is a noble gas atom, which means that once it gets to the surface, it likes to get electrons. It likes to be neutral. There's no element in the periodic system that can compete with helium. It's the highest electron affinity of all elements. And so, after penetrating, it becomes neutral. Okay, may scatter back. If it would stay neutral, I cannot see it because I need this zigzag in my analyzer, and I can only do that with electrostatic fields. So, but fortunately, there are thresholds, and above a certain threshold, there's a small probability to be re-ionized again. So, for instance, helium in a last collision with an oxygen atom, it can, above 700 volts, it gets re-ionized. And in that way, I can make visible deeper layers. And so when I scatter from zirconia, I have a surface peak, which is the top layer. And then the background, this tail, tells me how thick that zirconium layer is. It's just a friction force going whoop, whoop, whoop in, lose some energy on the way in and out, and it tells me how thick it is. And in the range of a few nanometers, we are extremely accurate in determining the thickness. Okay, summary for the moment. First summary is outermost layer, deeper layers, detection limits for the top layer. Light elements, we are not so very sensitive. So for lithium, it's only a few percent. But if you get to the heavier ones, say like platinum, about 10 minus 5 of a monolayer, so 10 parts per million of one atomic layer, we can see for heavy elements. Pre-chamber, so you can heat, you can do all kinds of things. Yeah, one important thing is sometimes we use an atom source for oxygen to remove organics. That means oxygen atoms, they evaporate, carbon will become CO, CO2, and you can clean up. Of course, here in Kyushu, the atmosphere is very clean, but still, I fear that you will have some contamination on your surface. Okay, start with the real applications. One of the applications is wetting or spreading of an active phase on a catalyst. So this is a case where there is molybdenum oxide on top of a rough silica surface, and by heating you see, if you heat, that the silicon signal goes down, it disappears completely, and the molybdenum goes up. What happens? Well, you start off with clusters of molybdenum oxide, and they just spread on the surface. They wet the surface. And so on a quantitative way, you see here, at the end, it's fully covered by molybdenum oxide, and there's no silica anymore. So wetting or de-wetting, that kind of processes are easy to follow. Another process that is very important is surface segregation. And this is an example where we looked at very high purity zinc oxide crystals. And so it is zinc oxide, and we look at the surface. First, sputter clean it, then you get oxygen, sodium, potassium, and a lot of zinc. And then you heat, and you have only to heat up to 100 degrees centigrade, which is, I mean, for ceramics, that's nothing. But at that time, sodium comes, whoops, and spreads on the surface. The enrichment at the surface is 8 orders of magnitude, a factor of 10 to the 8th. So you need extremely small impurities that you cannot detect with any other technique, but still they may become 100% sodium in the top layer. And so the chemistry and a lot of the properties may change a lot once you do that. First, I show you the bad examples, so the terrible things of contamination. This is an example of preparing a catalyst. And one of the ways of preparing a catalyst is that you impregnate them. And in this case, it was a catalyst, which is a very famous catalyst of molybdenum, vanadium, niobium, tellurium oxide for oxidation of propane to acrylic acid. And we looked at that catalyst and, well, silicon should not be there. You see a lot of elements, but not silicon. You don't see much of the other elements. What happens? The material, the isopropanol was the highest purity isopropanol you can buy, but it contains impurities. And so, when you do that, there's a little bit of siloxane in there, 10 ppm in the solution, and all the siloxane gets to these molecules. So, in fact, the surface is at the end mainly silica. And so your catalyst will behave very differently because of that. So you have to learn. If you do any other technique, generally I compare to XPS, but of course other possibilities. That gives of course a lot of interesting other information, but it looks much deeper. And because of that, they did not see, or they thought it was not relevant, the silicon. Here we say more than 50% of the surface is covered by silica. Okay. Spinels and perovskites are important mixed oxides that are used for many applications. I'll first show you something on spinels. They have the structure of, say, AB2O4. For instance, zinc aluminate. And when you do the ion scattering of a zinc aluminate, well, this is an old spectrum, so the statistics is not so good. Nowadays we do much better. But you see an oxygen peak, you see an aluminum peak, you see a background here, but no peak. What does that tell me? Well, if I have real zinc oxide, yes, I can see the zinc. But the zinc is not in the top layer, because then there would be a peak. It is just below. In zinc aluminate, the zinc atoms are half an atom down. And because of that, they cannot participate in the chemistry, and you don't see them in ion scattering. You only see them as a background. Or if I take an example which is a little bit more important for catalysis, I show you for things with cobalt. I have three different catalysts: cobalt aluminate, zinc cobaltate, and cobalt oxide. And you see that this is 1 cobalt, 2 cobalt, 3 cobalt. So you would think, I know what's going to happen. But here, there's almost no cobalt to be seen in ion scattering, and also the activity is almost 0. Here, there's a lot of activity, and it's the same as the 3. Why? Well, in red I have shown the elements that are at the surface, in black the ones that are just below. So that is why here there's no cobalt in the top layer, no activity. Here there are 2, and there are 2 as well, because the third one is below. So on a quantitative basis for Spinels, you can correlate catalysis with what you see and make better catalysts that way. You should realize this is not a single crystal. This is a powder. This is a real catalyst. So it is very rough. And although originally I thought you have all crystallographic planes and whatever, in practice there are only those planes that have the octahedral sites at the surface, and the tetrahedral sites, like here, are just below. If you do other techniques, and many techniques have been tried, but there you will, for instance, XPS, there is no correlation between activity and what you see, and in ion scattering you see there is. If you go to other things like perovskites, again there is a preference for certain cations to be on top and certain others that are not, and so it's important to be able to see that and improve your surface. Let me go to an example of solid oxide fuel cells and oxygen membranes. And why is it seems that the surface is important, but why is that the case? Well, this is a typical spectrum of yttria stabilized zirconia. So it's zirconia with a little of yttria. Now, when you look at well, this is a complicated spectrum, but what you see immediately here would be the peaks for yttria and zirconia. There is no peak. You see a lot of other things. Fluorine, sodium, silicon, calcium, hafnium, all kind of things at the surface, but no yttria and zirconia. And that is because once you activate this and go to the temperatures where the SOFC should work, impurities come from below and segregate to the surface. They kill the surface. It's only the top layer. The second layer is yttria and zirconia. And so you see the tail, the background here. Yes, there is a step because there is yttria and zirconia in the second layer, but not at the top. So if I plot in this case as a function of the amount of calcium oxide my signal, if I slowly heat up that SOFC, then I see that my coverage yttria and zirconia goes down and the calcium oxide goes up. Or if I go one step further, what we did is we did O16, O18 exchange, and that is a collaboration with the group of Professor John Kilner at Imperial College, and they recently, there was a very nice paper on oxygen exchange with ion scattering. You can see that you can easily separate O16 and O18. They're easy to measure and to separate, and so we use that to look at yttria stabilized zirconia, and you see that once there is more calcium oxide, the exchange of O18, when you expose it to O18, there's no exchange reaction anymore once you have 100% calcium oxide. So the calcium oxide is completely filling up one monolayer, and it stops the exchange with O18. And so that is bad when you are trying to make a fuel cell of it. So you have to do things, play tricks to reduce that amount of calcium oxide. I jump to a completely different application. Particle size. In catalysis, very often, well, you know that catalytic properties are dependent on the size of nanoparticles. Are they 1 nanometer, 2 nanometer, whatever. So you want to be able to measure that. Now, the bigger ones are fairly easy to do with transmission microscopy, a very reliable and good technique. Sometimes people do chemisorption, and so we have had a collaboration with the people of Johnson and Matthey and people Tanabe, who's now at Toyota here. We combine these techniques with low energy ion scattering, and I'll show you how we can determine, or how I should say you next month or early next year can determine the size of these clusters. Well, if this is a real catalyst, a kind of cartoon, small clusters on top, something very rough. So if I look at one of these nano clusters, in ion scattering I will see the top layer. If I use a bulk technique, a chemical technique, how much platinum there is in total? I know the volume, here I know the surface, and the ratio of volume to surface gives me the diameter. And so, in this case, we looked at real three-way catalyst with a normal loading of so much platinum on gamma alumina, and we determined that the diameter of this cluster is 1.6 nanometer. That is reproducible and accurate. Especially for small clusters, it's easy to measure because there's more surface area. It's easier. So especially in cases where the clusters are small, it's difficult to do that with transmission electron microscopy, generally below 2 nanometer. It's really difficult. And also TEM is difficult if the support, like this one, it has cerium and other things. It's very difficult to measure sizes of tiny platinum clusters. But by just measuring the signal, you can determine the average cluster size. And of course, what we do is not only just platinum, it's of course real fun to do core shell particles where you have, say, a few nanometer particle where the outside differs from the inside. And so you can determine, is it a real closed shell? How thick is that shell? And so we help to develop new catalysts. Another example. Since probably many of you are chemists, then, and I'm a chemist originally by training, then you say, well, okay, it's nice, good to know that there is platinum or gold, or in this case, there is things like copper or zinc in a special methanol synthesis catalyst. That's great, fine, and it's important. However, what we are really interested in is what is the oxidation state. And normally you would say, okay, then we go to other techniques, like, for instance, a very powerful technique, XPS. However, there's also a problem. When you do XPS, you get the oxidation state, which very high accuracy, but averaged over many atomic layers. And what you would actually like to know for a catalyst, what are the oxidation states in the top atomic layer? Now, in ion scattering, we just get atoms only. So, what do we do? Well, there is a third technique, which is not, it's a very complicated one to do it accurately, is chemical titration. So you expose the surface to something like N2O, and you see how many oxygen atoms you can use to oxidize. Of course, you may oxidize the top layer, but also the second and the third layer, and you oxidize the copper and the zinc, and it's not so trivial. Now, what I suggest is to combine these two techniques. And so, on the one hand, I use ion scattering to look at the top layer. On the other hand, I use chemical titration to change the oxidation state. And now you should realize that if I have metallic copper, it's very easy to scatter from it and I get a high signal. If I oxidize copper, it is partially surrounded, screened by oxygen atoms. Because of that, I lose a factor of 4 about if I oxidize copper. So, all I have to do is, if I have a complicated catalyst, I measure after preparation, after activating the catalyst. I see a copper peak and perhaps other things if there is. And then I oxidize and I see how far the signal of the copper and the zinc decrease. If they stay the same, they were already in the highest oxidation state. If they get lower, apparently they were more in a lower oxidation state. And in that way, you can determine the oxidation state of this catalyst. And this is an example where we did that on a real catalyst, and we used, there's the Topsoe company that is very famous for this kind of catalyst. They helped me to get the right chemistry to prepare the catalyst. And you see here, I show you the oxidation states of copper and zinc for two different temperatures. And of course, when you go to higher temperatures, it sinters, the clusters get bigger, and you get a different oxidation state. So you get the oxidation states of these elements, element specific for the outermost atomic layer. And that's fun. Other thing. In chemistry, you are always interested in what is the active site. Well, generally we don't really know very much about the active site. But sometimes you need more than one center next to each other. So we looked at catalysts where, for instance, you need two vanadium cations close to each other with a certain valence state. And so how can you find out whether they are far away or next to each other? And one of the ways you can do that is by using probe molecules. And these probe molecules, so for instance, I can use either methanol or allyl alcohol. Methanol absorbs just anywhere, so not really fun. The signals of all elements disappear. But with allyl alcohol, it needs two sites. And because of that, you can find out how many of these vanadium cations are close to each other. So close that an allyl alcohol can bind to both of them at the same time. And when it absorbs, I have monolayer sensitivity. When it sits on top, I don't see what's below. So by the change, it reveals by with and without the molecule. With the molecule, I don't see what is below. And so this way helps me to learn things about the activities. I'll do quickly I started off with the example of zirconia on silicon. And in general, when you grow things like this zirconia on a silicon wafer, when you grow more and more and more, the coverage goes up, so you get more and more zirconium. But you will see that, well, even in the red one, there's still something missing. And this is an accurate technique. So if you miss that, you say, there are still pinholes in the layer. It's not a complete coverage yet. However, you will see already for red that there is an asymmetry. Normally these peaks are Gaussian. Here you see there's a tail. Why is there a tail? Because there is not only in the top layer, but there is also in deeper layers. So it starts to nucleate in various places, grows in hills, and finally, and only here, after this goes in cycles, after 100 cycles, it is fully covered. And so we use that to learn about growth processes and help especially the microelectronics industry to get very well defined ultra-thin layers. And depending on how good your chemistry is, you do it in cycles. If you are very lucky, in a few cycles you can get closure. Very often you need many cycles, which means I have big mountains and there are still pinholes at the same time. And so that is not good. Let me see. So this is an example with IBM where we got better. And so what we do is you can look at the initial growth, because you look one atom deep. You'll see when the film gets closed, whether there are pinholes. And poisoning is a very important one. I would like, because I'm here, like to, sorry, I'll just go for a second to this one. In catalysis, one of the important things is coke formation. And coke formation is always terrible. Now, you could say any technique, any surface technique will show that there is carbon on the surface when there is coke formation. Simple. But what you like to know is, where is the carbon? Where does it start, that coke? Is it just anywhere? Is it at support? Is it the active phase? And sometimes it's even something different. And so by looking at what your signal, how it depends on coke formation, which elements disappear, you know where it goes. And if you don't believe it, at the end, you treat it with atomic oxygen at room temperature, and then the signals come back again. So this is a way to learn about nucleation of coke. And we do that for a lot for exhaust, catalyst, and other things. If I go back just a second. Okay. For polymers, one can do a lot of work on polymers. And this is a case where to make OLEDs or PLEDs, whatever you call it, you make a metal contact on a polymer, and if it would just evaporate on top and form a monolayer, you should get a nice, like the blue one, a nice Gaussian peak. For instance, for barium on a polymer. In practice, you will see the red one, it is very wide. Why? Because it's not only on top, but as you see here, it diffuses into much deeper layers. Now, the amount of light that you get out of an OLED depends on the sharpness of that interface. So once you can measure this, we use that in situ to optimize our process to get better sharp interfaces. And in that way, we could gain about a factor of 3 higher light output by having a very sharp interface. So there's a lot of work, in fact, also in polymers where you can use this technique. Like, I'm close to my time, where you do, for instance, say, self-assembled monolayers. You can see whether they are standing up, what the thickness is. In this case, it's fluorinated thiol on a gold which is a very simple one. If it was just gold on top, you would get this peak with a little bit of background for gold in deeper layers. When we put the thiol on top, this peak disappears. And if I amplify this by a factor of 50, I see there's an onset. That shift tells me whether the layer is 11 angstrom thick, or in the other case, it's only 7 angstrom thick. That shift is very characteristic for the energy loss going through that layer in and out. And so you can determine with the accuracy of about 1 carbon atom how thick that layer is. Okay, let me summarize. Why do you need this? Well, the fun is you can do it any temperature, any material, quantitative, etc. You can look at segregation, anti-wetting. I showed you some examples. You can look at pinholes. For catalysis, I showed you poisoning. I did not show the promoters because they are generally confidential, so I don't talk about it, but we do measure them. Probe molecules, core shell nanoparticles, etc. Something about nanoclusters, oxidation states in inorganics, and of course all kinds of things like cleaning strategies for the semiconductor industry. And you should realize that this technique is very complementary to the other techniques, and so one technique cannot solve all problems. You need a combination of other things. So very often we combine it with XPS and TOF sims, but this is a little unique for the outermost layer. Thank you very much.